Hello and welcome to the first lesson of Unit 7, which is all about exponentials. Today in our lesson, we are going to be graphing exponential functions with transformations. So let's get down to business. A couple definitions for today. An exponential function, it is a function in which the independent variable is an exponent. An asymptote is a line that a graph approaches. Exponential growth. It's going to look like this, and we'll talk about it later. Change that occurs when an initial amount increases by the same percent over a given period of time. Exponential decay, it means it's going down. So it's when the initial amount decreases by the same percent over a given period. And a decay factor is when we have 1 minus r. So we will eventually talk about transformations, but first we want to go over parent functions. These are going to be our starting values. So this first function, this is going to be exponential growth because our b value is going to be greater than 1. So creating that table of values, 2. When we plug them in, 2 to the negative second power, we want to make it positive, and so we would get 1/4. 2 to the negative first power, again, we want to send it to the bottom, and so we would get 1/2. Anything to the 0 power is 1. Anything to the first power is itself, and 2 squared is 4. You should kind of see a pattern that these numbers are reciprocals of each other. That is not a coincidence. And so when we graph these points, we got -2 1/4, -1 1/2, 0 1 1 2, and 2 4. We could even graph another one, 3 8, since we have so much space. And so when we connect them, our graph should be pointing up. It is going to have arrows on both sides. Now we do have this thing called an asymptote. That is where our graph approach. It is a dashed line because we use it as a guide. And so for this problem, our asymptote is going to be y equals 0. Our y-intercept, where does it cross the y-axis? It is at 0, 1. Our domain is -infinity to infinity. It will always be this no matter what. And then our range is going to be parentheses 0 to infinity. The reason we have a parenthesis on it is because of that horizontal asymptote. We'll never hit that asymptote, and so that's why we don't use a bracket. Okay, so that's our first parent function. That's our exponential growth. Now let's look at our next one. This is going to be exponential decay, and that's because b is between 0 and 1. And so if we set up our x and our y values, we're going to use the same y values on the other page. What's kind of cool is that you can find them pretty quick. 0 always maps to 1 because anything to the 0 power is 1. 1 always maps to our base, so 1/2. And then 2 maps to that squared. We can then do the reciprocal of them to get our parent function values very quickly. And so when we graph these, we got -2 4, -1 2, 0 1, 1 1/2, 2 1/4. I guess we can throw in that -3, 8. And so now when we connect them, we're going to have our graph go like this. And again, we still have that horizontal asymptote. It's also going to be at y equals 0 because that's where our graph is approaching. And so our y-intercept is going to be, well, and behold, the same thing. Domain is the same, and our range is the same. And that's because it's a parent function. Not a lot's going to change. The only thing that's going to change is if it's growing or if it's growth or decay, and the values on either side of the y-axis. Okay, so now that we have that, let's go on to the next page where we can define our transformations. So we have our A value, which is a vertical stretch. That's if your A value is greater than 1, or a shrink. That's if A is between 0 and 1 by a scale factor of A. Now, if we have a negative A, that is our reflection over the x-axis. We then have b to the x power. This is not a transformation. It is our parent function. It's what we use to set up our table of values. We then have our h value, which is our horizontal shift. You can just say left or right. Just remember that this is going to be your opposite. And then finishing with that k value, this is your up or down. Now, this will be the same. It's also going to be your horizontal asymptote, which your asymptote, again, is going to be y equals k. The reason it is because that line can only move up or down, and it's our y value. Okay, so let's do some graphing. Here we go. We have a reflection over the x-axis. That's that negative. I'll color code for today. Whoa, not that color. Let's try this color. There we go. Okay, and then we have that 2. That is that vertical stretch by a scale factor of 2. That's the 2 out in front. That 3 to the x power, that's our parent function, 3 to the x power. If you struggle, all you have to do, find x, the number attached to it is your parent function. What isn't a parent function is that plus 4. This is a left, because we do opposite, left 4, finishing with that minus 1 that is outside our exponent, and so that would be down 1. So our horizontal asymptote is going to be at y equals negative 1. Now, personally, before anything, I like to graph that asymptote on my graph, so it helps me kind of guide my function. So now what we're going to do is we're going to set up our table. So negative 2, negative 1, 0, 1, 2. 0 always maps to 1. 1 always maps to our base. And 2 maps to that squared. So 3 squared is 9. Now we're just going to do the reciprocal to get more values. From here, whatever is outside, so I'm going to fill my table in as I move left to right. So I've got a negative, because I'm going to change my sign. I'm then going to multiply by 2, going to the other side, because that plus 4 is inside the exponent, so we do the opposite. And then finishing with that minus 1 on the y side. From here, I get negative 6, negative 5, negative 4, negative 3, and negative 2. I'm going to change all my signs. Now, a big thing people struggle with is that the table is not really worth anything. It is a guide. So when I multiply by 2 here, I'm going to leave it as a fraction. You can turn it into a decimal. Your choice, it depends. So like I'm going to say, oh, this is going to be negative 1 point. I think it's technically, I think 2 repeating, but I'm just going to write negative 1.2. This is going to be negative 1.6, negative 3, negative 7, and negative 19. And so just like with all of our other transformations that we've done so far, is we're going to graph our outermost columns. And so I know the graph is weird. It was just the easiest one. So we have negative 6, negative 1.2, negative 5, negative 1.6, negative 4, negative 3, negative 3, negative 7, where are we at right here, and negative 2, negative 19, which is all the way down here. So then we can connect our points to get our graph. Now, our graph should always be on either the top or the bottom of your asymptote. And so I know it's kind of on 2 pages. So our asymptote for this one is y equals -1. Our y-intercept, well, think about the fact that a y-intercept is always 0, y. We can plug in 0. So like for this problem, it's not on there. We can plug in 0 for x and see what happens, and we would get -163. Now, sometimes it'll be given to you on the graph. In this case, it wasn't. So our domain is -infinity to infinity, and our range, because of that reflection, is going to be -infinity to -1 with our parenthesis. That asymptote will always show up in our range because it's either going to be the bottom of our graph or the top of our graph. Okay, we're going to do one more practice problem together. So here we go. So we have that vertical stretch by a scale factor of 4. That 1/2 is our parent function, and we know that because the x is attached to it. Then we are, right 2, and then up 3. So again, I'm going to draw in my asymptote at 3, just so that way if I have points on both sides, the top and the bottom of that asymptote, I did something wrong. Okay, here we go. So we've got x and y, -2, -1, 0, 1, 2. We are using that parent function, which was on the other page. So 0 maps to 1, 1 maps to 1/2, 2 maps to that squared. I'm going to do the reciprocal to get my other values. Then filling in my table, I'm going to multiply by 4, add 2, and add 3. And so filling this in, we would get 0, 1, 2, 3, and then 4. To the other side, we would get 16, 8, 4, 2, and 1. And then adding 3, we would get 19, 11, 7, 5, and 4. And just like everything else, we are going to graph those outermost columns. And so we're lucky on this one, our y-intercept is identified. 0, 19. Then we have 1, 11. What else? 2, 7. So right here. 3, 5. And then 4, 4. This is why I like that asymptote, because it's going to help us when we draw, when we connect our points, that our arrow should be approaching that asymptote. And so, finishing everything on the other side, we are going to have y equals 3, y-intercept is 19, our domain is -infinity to infinity, and our range, because there was no reflection, is 3 to infinity. Now, you can write your y-intercept as 0, 19. Both ones work. Okay. I would appreciate if you stopped the video right now and tried example 2. Hopefully you did pause it. And so here we go. We get y equals 4 to the x power is our parent function. We have a reflection over the x-axis, a vertical shrink by a scale factor of 1/2, I keep doing that. We go left 4 because it's opposite, and then down 2. And so I'm going to draw in that asymptote real quick. That asymptote, remember, is right there. And so we got x and y, -2, -1, 0, 1, 2. 0 maps to 1, 1 maps to our base, which is 4, 2 maps to that squared, and then I'm just going to do the reciprocal of those values. From here, we got a reflection, a shrink, a shift, and another shift. And so when we plug those values in, we would get -6, -5, -4, -3, -2. Changing those signs. And there we go. And then I'm going to multiply by 2. I'm going to write this as a fraction just because I can personally do it faster, or as a decimal. It doesn't matter. Whatever makes your brain happier. Then I'm going to subtract 2, so I think this is like negative 2.0, let's just 0.1, negative 2. Let's say 1, negative 2.5, negative 4, and negative 10. Again, with those decimals, we're just trying to get as close to that number as possible to get a guide to graphing it. And so when we graph this, we got negative 6, negative 2.1, negative 5, oopsies, 2.01, negative 5 is negative 2.1, negative 4 is 2.5, then we got negative 3, negative 4, and then negative 2, negative 10. And so we connect them to get this as our graph. And so our horizontal asymptote is y equals negative 2. Our domain is negative infinity to infinity. Our range, because of that reflection, is negative infinity to our asymptote, which is negative 2. Make sure we have a parenthesis on our range. And then I'm going to plug this into my calculator. And I got my y-intercept as negative 130. Okay. Next page, or not next page, just to figuring out if it's growth or decay, all you have to do is look at your b-value. It's growth if your b-value is greater than 1. It's decay if your b-value is between 0 and 1. Exponential, you just got to make sure you have an exponent that's a variable. And so, here we go. A is growth, because 5 is greater than 1. B, decay, because 2/7 is between 0 and 1. C, this one's tricky. It's growth because 4/3 as a decimal would be 1.3 repeating, which is greater than 1. D, also growth because 1.05 is greater than 1. E, this is decay because 0.85 is between 0 and 1, finishing with F, which is also growth because 16 is greater than 1. All you're doing for your base is looking at the number attached to the exponent. So like for example, example 2, this would be a growth problem because your B value is greater than 1. Even though it looks like decay, that's because when we transformed it, we reflected it. Okay. Now we're going to look at some word problems. Here we go. So what does it mean when something grows, and how do we think of this in math? I want you to take a moment and try these two on your own, and we're going to talk about them in class. But exponential growth and exponential decay. Our formulas for exponential growth is 1 plus r. Now, r is your rate. We do have to turn it into a decimal because it'll be given to you as a percentage. Where this is coming from is if we turn it back into a percent, it's taking 100% and adding on your rate. The 100% is your original amount. And so exponential decay is 1 minus your rate because you're decaying, you're decreasing the value. And so that's where that 100% minus your rate as a percentage is coming from. So for example 4, Izzy purchased a car in 2025 for $26,000. It depreciates, this word means decay. It goes down in value at a rate of 13% each year. How much will be the car be worth after 1 year? And it says round to the nearest cent. This is 2 decimal places if you don't know. Decimals. Okay, so using that formula, because it depreciates, we're going to use that exponential decay. So y equals our A value, our starting amount. What did we start with? $26,000 times 1, well, depreciate, so minus rate. Now, big place, people will make mistakes. They'll just put 13. We have to turn that 13% into a decimal. So we move it once, twice over. So that's where we get that 0.13 to the first power. Now, we do want to simplify this if we were asking for an equation. And so we would get 0.87 to the first power. Now, when we plug this into our calculator, oopsies, 2600, I would suggest practicing this right now because I will not help you. We get a whole number, $22,620. We don't want to forget our unit because we're working with a word problem. Next problem, B. How much will the car be worth in 2030? Well, it was bought in 2025, so this means that 5 years has passed. So when we take that equation, we're going to plug in 0.87 to the fifth power, which will give us, this one's going to be a decimal, so 12958.9439. And so, because we have to round to the nearest cent with our units, we're going to end up with $12,958.94. The reason is we look at that 3 to see if we need to round up or round or keep the same. Okay, let's try example 5. Gavin bought a semi-rare hockey card for $120. So that is our initial amount. The value is expected to increase, so that's going to be growth by 4%. So our equation is going to be y equals 120 times 1 plus. Now again, we have to take that 4% and turn it into a decimal. So we're going to add 0.04 to the t power. And so our official equation would be y equals 120 times 1.04 to the t power. This goes back to what we saw in our previous page on example 3. Our b value is greater than 1, so it's growing, which supports the fact that it's increased. So now what we're going to do is we're going to take that equation and we are going to plug in 8 years into the exponent. So 120 times 1.04 to the 8th power. We again get not a nice number, so 164.22828. And so I'm going to look at my third decimal place to see if I need to round up or keep the same. We are going to round up to $164.23 based on the 8 rounding up. Okay, here we go. Last page, last problem. Here we go. On New Year's Day, Charlie begins a savings plan. She saves $1 the first day of January and increases the amount she saves each day by 1%. So what is our growth factor? This is our B value. So because it's increasing, we would do 1 plus, now 0%, or 1%. We need to turn this into a decimal. So again, we move it once, twice over. And so we're going to do 1 plus 0.01. And so our B value is 1.01. Woo! Now we can write our equation. So y equals our starting amount, 1, times 1.0 to the t power. Now, if you want, 1 times anything is itself. So you could write it as this. I'll take either one. And so now what we're going to do is we're going to find out how much she'll have in 1 year. Now, you got to be careful. We're not going to plug in 1. That wouldn't make sense. What we're going to instead plug in is 365 because, assuming it's not a leap year, there are 365 days in a year, and we're changing the amount every day. And so when we plug this in, 1.01 to the 365 power, we get 37.7834. And so again, we're going to look at that third decimal place. We keep it the same. So we end up with $37.78. Okay, so come with your questions to class. I hope you understood it.